Mechanics static. A problem about a hanging chain, which called catenary. A chain with a uniform mass density per unit length hangs between two given points on two walls. Find the general shape of the chain. Aside from an arbitrary additive constant, the function describing the shape should contain one unknown constant. So, first important fact here is to note that horizontal component of tension T, it's a constant on all this chain. Because if we take any part of this chain and it's in equilibrium, there are no external horizontal forces, so it means that the tension, horizontal tension in this point exactly equal horizontal tension in this point. And let's do this Tx equal this constant C. Now let's describe this shape of this chain as a function y x. Because this chain has this shape and tension always direct as a tangent to this chain, we can write that T y over Tx, that's just equal first derivative from function y. And because Tx is constant, we can write that Ty just equal C y prime. So now let's take a small piece of this chain, like on this picture. We can write this equation that delta Ty, the change of vertical component of tension, that's equal to length of this part multiplied by rho and multiplied by g. So we can write it in form dx root 1 plus y prime square. And we can rewrite this formula in the form of delta T y of the delta T, that's equal rho g root 1 plus y prime square. But this function Ty exactly equals this function. So we can rewrite this formula in form of y second derivative, that's equal multiplied by c, that's equal rho g, and root 1 plus y prime square. Now we can substantiate y prime as a new function z and rewrite this equation in form of c z prime equal rho g root 1 plus z square, or we have this expression that d z over root 1 plus z square, that's equal rho g over c. And now we have this equation, and we can do integral for both parts, and the integral from this part equal dz over root 1 plus z square. That's equal to reverse hyperbolic sine z plus some kind of constant a, or we can write this equal to constant a plus rho g over c x. So we can make this formula, this equation look a little more clear if we take nu alpha equal rho g over c, and a equal a constant a over alpha. In that case, we can rewrite this formula in form of z equal hyperbolic sine from alpha x plus a. So this is the formula. And last step, in our case, z, this is just y prime, and we can integrate this formula again, and finally we have that y equal 1 over alpha hyperbolic cosine from alpha x plus a plus some kind of other constant h. So we just found that our curve has looks like a hyperbolic cosine, and we can just imagine that this cosine has minimum exactly in point x equals 0, and we can let h equal 0. In that case we have total shape equal 1 over alpha cosine hyperbolic cosine alpha x. So this is the solution for the first part of this problem. Next problem, we need to find what is this coefficient alpha if we have distance between walls is d, the height difference between 2 points is lambda, and the length of our chain is L. So we need to find what is coefficient alpha. Suppose that our midpoint is right in x equals 0. So it means that left point has coordinate negative x0, which is unknown, and right point has coordinate d minus x0, and we know that now we need to find these two parameters x0 and lambda. So first expression, the height difference can give us this expression that y in point d minus x0 minus y in point negative x0 and just equal lambda. That's one expression. And the other expression is that total length of this curve is L, which is integral from 1 plus y prime square dx from point negative x0 to d minus x0. That's equal L. Rewrite this in terms of our functions. This equation we can rewrite in form of hyperbolic cosine in point d minus x0 minus cosine hyperbolic in point negative alpha x0. That's equal alpha lambda. That's one equation. This we need to count. So we have integral from negative x0 d minus x0, and here we have a first derivative from hyperbolic cosine. This is just sine hyperbolic, and that will be root from 1 plus hyperbolic sine square from alpha x dx. And we know that 1 plus hyperbolic sine square, that's just hyperbolic cosine square, and square root, that's hyperbolic cosine, and the integral from hyperbolic cosine, that's just hyperbolic sine. And finally we have this expression. This is 1 over alpha hyperbolic cosine from alpha x from negative x0 to d minus x0. And we can rewrite this in form of oh, that's not cosine, this is integral from cosine, that's sine, hyperbolic sine. And finally this equation we can represent in form of sine alpha d minus x0 minus sine minus alpha x0, which is equal to alpha L. So we have two equations, this one and this one. Let's rewrite them. So we have these two equations, and we have two unknowns, x0 and alpha. We have to eliminate x0. For that we just square this equation, square this equation, and subtract from this, and use a formula that cosine hyperbolic square minus sine hyperbolic square, that's equal 1, and hyperbolic cosine u multiplied by hyperbolic cosine v minus hyperbolic sine v multiplied by hyperbolic sine u. This is just equal hyperbolic cosine from u minus v. So we use these two expressions to eliminate this x0. We square this equation, square this equation, subtract from this one, and using this formula we finally find that 2 cosine alpha d minus 2, that's equal alpha square multiplied by L square minus lambda square. And we can rewrite this in form of 2 sine alpha d over 2 using a formula for half angle. That's equal alpha root L square minus lambda square. This is the equation how to calculate parameter alpha numerically, because it cannot be solved in like regular functions. So this is the solution.